here. I'm with you. I'll be there in a minute. How's everyone doing tonight? Okay, I think it's okay to start. What do you think? Do you think it's okay for us to start? Oh, why doesn't the sound play? What? Sorry about that. I'll have to figure out what that was about at a later time. But welcome everybody to the stream. Let us get to our scene. There we go. Look at that, we got Proxmox. Let me log into the Proxmox server and see what's going on with that. Because root doesn't have multiple. Yeah, see. Okay. So we have Windows 7, Jellyfin's running, Debian's running. Blogger post. I think that we're going to move away from Blogger. So what do we want to do today, guys? What we want to do today is to continue on with the learning of the C programming from the Beeges guide. So let's get Emacs up here, and we can continue. Emacs client. There we go. There we go. There we go. Okay, so there's our learning, and here is our terminal, which we don't even actually need for right now. Let me actually close. Let's close this. Close this. Because I want to see. Can I run the daemon? Emacs. Daemon. Did not start. Another instance is already running. So how do I kill it? PS. All. I don't know. Man PS. To see every process uses the standard sense E. PSE. Oh, okay. PSE grep Emac. Emacs, there we go. Kill 9343. There we go. Okay. So now I forgot that it was E. E is for all the processes. Emacs daemon. Starting Emacs daemon. Okay. Now we can do Emacs client and R and there we go. Okay. So we're gonna work on some Emacs configuration as well, just quickly to get customize theme. Live in dark is what I've been using, right? Okay. So now if I go to, we should see live in dark. No, it didn't add it. Do I go back? Oops. Let's go to It's not playing our music? Where's our music? Oh, there it is. Have I been on... Oh, I'm so sorry. I think I've been on the... It's Friday! Friday fun day! I think I was on the wrong thing the whole time. My apologies. Forgive me. You must forgive me. Okay, so... let's go back to the... custom themes. Okay. Alright, so let's go into the learning. We'll look at doing the other stuff later. Okay, so what we left off was with some struct caveats off of the binary. So we did the binary bin output and the bin input. File for reading. Okay, and then we did the reading output with practice read, bin input. So we could go to we could say let's do bin input. There we go, and that reads out the binary of the files, and I put in 9565. And then there's a caveat here. As we saw in the struct section, let me turn the music down just a little bit. Okay, that must be better. Is that better? As we saw in the struct section, the compiler is free to add padding to a struct as it sees fit. And different compilers might do this differently, and the same compiler on different architectures could do it differently. And the same compiler in the same architectures could do it differently. So they're talking about Indianness here. But if I run it, that has to do with called Indianness of the architecture. Some write the most significant bytes first, and some the least significant bytes first. That means that if you write a multi-byte number of strings, you can do it in a portable way. You can't do it in a portable way. A similar problem exists with floating point. Most systems use the same format for their floating point numbers, but some do not. No guarantees. So how can we fix all these problems with numbers and structs to get our data written in a portable way? The summary is to serialize the data, which is a general term that means to take all the data and write it out in a format that you control, that is well known and programmable to work the same way on all platforms. As you might imagine, this is a solved problem. There are a bunch of serialization libraries you can take advantage of, such as Google's protocol buffers, out there and ready to use. They will take care of all the gritty details for you and even will allow data from your C programs to interoperate with other languages that support the same serialization methods. Do yourself and everyone a favor. Serialize your binary data when you write it to a stream. This will keep things nice and portable, even if you transfer data files from one architecture to another. When you write it to a stream. So when you're doing your data files. When you're doing your DAT files. Okay. Type def. Now we're going to type def. Type def, making new types. We'll not so much make new types as getting new names for existing types. Sounds kind of pointless on the surface, but we can really use this to make our code cleaner. Type def in theory. Basically, you take existing type and you make an alias for it with type def, like this. Type def int antelope. Make antelope an alias for int. Antelope x equals 10. Type antelope is the name as type int. You can take any existing type and do it. You can even make a number of types with a comma list. Type int, antelope, bagel, and mushroom. These are all int. That's really useful, right? That you can type mushroom instead of int. You must be super excited about this feature. So, can I do... Where is hello? Hello. 1, there a hello there? Just the text. Where is our first strings, I guess? So I can go here and I can say type def static. Oh, but that's not. No, because that would be a define, right? Internal, global, internal, global. Does that work? Recompile. Oh, we don't have a compile. GCC minus standard equals C89 minus wall minus extra minus pedantic minus O strings dot C. Type def defaults to int in declaration of internal. Type def static internal global. Oh, because you have to have a thing there. Recompile. Multiple storage classes and declaration specifiers. Type def static. Oh, okay. So because it would be defined. Okay. That's really useful, right? That you can type mushroom instead of int. You must be super excited about this feature. Okay, Professor Sarcasm. We'll get to some more common applications of this in a moment. Scoping. TypeDef follows regular scoping rules. Did we talk about scoping yet? I guess. For this reason, it's quite common to find TypeDef at file scope global so that all functions can use the new types at will. TypeDef in practice. So renaming int to something else isn't exciting. Let's see where TypeDef commonly makes an appearance. Typedef in structs. Sometimes a struct will be typedef to a new name so you don't have to type the word struct over and over. Struct animal, char, leg count, speed. Ah, okay. So let's do that then. Let's do animal.c include H, our normal stuff here. Return 0. Okay. And we're gonna make a struct animal. Char name, int leg count, and speed. Don't need a leg count and speed. And then we get typedef. Typedef the struct animal to animal. Oh. And then I could make a new one. Animal dog dot name equals Hootsen Flutsen is his name. Hootsen Flutsen. And dog dot leg count equals 4. He has 4 legs. Printf %s has %d legs. animal and animal.c. Okay. And then let's do animal here. Hootsin Flutesin has 4 legs. Yes, he does. He's a Flutesin. That's why. He's a Flutesin. All Flutesins have 4 legs. But he needs a thingy here. Then we can recompile. And we'll go back to ANSI term. Hootsin Flutesin has 4 legs. Him's a Hootsin. Him's a Flutesin. And he has 4 legs. How's everybody doing today? I am being silly. That is completely fine, though, isn't it? Okay, so we saw that. Personally, I don't care for this practice. I like to clarify the code. I like to clarify the code has when you add the word struct to the. I like to clarify the code has when you add the word struct to the type. Programmers know what they're getting, but it's really common, so I'm including it here. Now I want to run the exact same example in a way that you might commonly see. We're going to put the struct animal in the type def. You can mash it all together like this. That's exactly the same as the previous example, just more concise. Can you do that though with C? Can you do that with C90 or C89? Can we do it? Let's see, animal. Can we do it? Can we do it? And recompiling. Oh, you can. You can. That's very cool. Then I will do that. And it's the same output. Same output. Same output. Same results. That is really cool. People just join the stream and then they leave the stream. They join the stream and then they leave the stream. I don't know what I'm going to do with myself. I'm so sad that you guys aren't hanging out with me. Okay. But that's the exact same as the previous example, just more concise. But that's not all. There's another common shortcut you might see in code using what's called an anonymous structure. It turns out you don't really actually need to name the structure in a variety of places, and the type def is one of them. Let's do the same example with anonymous structure. It has no name. Okay. Forward. Delete. So, do we get to do this though? We do. We do get to do it. We're allowed to do it. That's good. Alright, so as another example, we might find something like this. Type def struct. Point, yeah. Okay, so that's the animal. I like it. Type def and other types. It's not that using type def with a simple type like int is completely useless. It helps you abstract the types to make it easier to change them later. For example, if you have a float all over your code in 100 zillion places, it's going to be painful to change them all to double if you find you have to do that later for some reason. But if you prepare it a little with type def float, app float, and app float, F1, F2, F3, then if later you want to change to another type, like long double, you just need to change the type def. Oh, okay. Okay. But, yeah, I don't know if I like that. Okay. Then if you want to change to another type, you just use type def. Type def and pointers. You can make a point. You can make a type that is a pointer. Type def int pointer. Int a, int pointer x, int pointer is type int pointer. I really don't like this practice. It hides the fact that x is a pointer type because you don't see a star in the declaration. In my humble opinion, it's better to explicitly show that you're declaring a pointer type so that other devs can clearly see it and don't mistake x for having a non-pointer type. But at least, at last count, say 832,000 people had a different opinion. type def and capitalization. I've seen all kinds of capitalization of type def. Lower snake case, camel case, leading uppercase, upper snake case. The C11 specification doesn't indicate one way or another and shows examples in all uppercase and all lowercase. K and R use leading uppercase predominantly, but show some examples in uppercase and snake. If you have a style guide and you stick with it. If you don't, grab one and stick with it. I think it would be capital case for types for my stuff. Arrays and type def. The syntax is a little weird, and this is rarely seen in my experience, but you can type def an array of some item, number of items. Type def int 5 ints. 5 ints x. I don't like it because it hides the array nature of the variable, but it's possible to do. Yeah, I agree as well. Pointers 2, arithmetic. Time to get more into it with the number of new pointer topics. If you're not up to speed with pointers, check out the first section. Pointer arithmetic. Turns out you can do math on pointers, notably addition and subtraction. But what does it mean when you do that? In short, if you have a pointer to a type, adding 1 to the pointer moves to the next item of that type directly after it in memory. It's important to remember that as we move pointers around and look at different places in memory, you need to make sure that we're always pointing to a valid place in memory before we dereference. If we're off in the weeds and we try to see what's there, the behavior is undefined and a crash is a common result. This is a little chicken and eggy with array pointer equivalence, but we're going to give it a shot anyway. Adding to pointers. First, let's take an array of numbers. Okay, let's do we have pointers on here? No, we don't. So let's just make a pointer. C. Standard IO. Let's make our main function void return 0. Okay. And then we'll do some 11, 22, 33, 44, 55. Okay, then let's get a pointer to the first element in the array. Okay. Int star p equals a. Yeah, because a is just going to be a pointer to it. Yeah, so I could also do the address at. Right, because is equivalent. Then let's print the value there by dereferencing the pointer. Printf %d n p. Now let's use print arithmetic to print the next element in the array, the one at index 1. Printf %d pointer arithmetic. Okay, so you do the arithmetic within the pointer there. Okay. Interesting. Interesting that you do it that way. I like it that way. I think we should do it that way. Prints 22. What happened there? C knows that P is a pointer to an int, so it knows the size of an int, and it knows to skip that many bytes to get to the next int after the first one. In fact, the prior example could be written these two equivalent ways. Oh. Because adding 0 to a pointer results in the same pointer. Yeah. So that's finally the first time I've kind of really understood that. Yes. Grok, finally. P plus 0 is the same pointer. Compile. Do pointer.c. Yes, I did mean that. Yes, I did mean that. Fancy term. Term. 11:11:22. Cool. Okay. Because let's think of the upshot here. You can iterate over elements of an array this way instead of using an array. Int p same as pi, and that works the same as if we used array notation. Ooh. Getting closer to that array pointer equivalence thing. More on that later in this chapter. But what's actually happening here? How does it work? Remember from early on that memory is like a big array, where a big array byte is stored at each array index, and the array index into memory has a few names. Sorry. And the array index into memory has a few names. Index into memory, location, address, pointer. So a pointer is an index into memory somewhere. For a random example, let's say a number 3490 was stored at address index 23,237,489,202. If we have an int pointer to that 3490, that value of that pointer is 23,237,489,202, because the pointer is the memory address. Different words for the same thing. And now let's say we have another number 4096 stored right after the 349 at an address 23,237,489,210. 8 higher than 3490 because each int in this example is 8 bytes long. If we add 1 to that pointer, it actually jumps ahead size of int bytes to the next int. It knows to jump that far because it's an int pointer. If it were an float pointer, it'll jump size of float bytes ahead to get to the next point. So you can look at the next int by adding 1 to the pointer, the one after that by adding 2 to the pointer, and so on. So this was the size of the pointer 8 bytes? Because it says that 8 in this example is 8 bytes long. So its point is size of P is 8 bytes. Four. So, is this a 32-bit system? No, they don't have 32. No, I should say size of star int. Oh, I guess that is that. What am I? So is this telling me that if we add 1, it actually jumps ahead bytes? Because of that, is it just that example? Because it's 32 bits, or 32, right? Size of int. Yeah, 4. So, but a pointer, the address, the size of the address is 8 bytes, right? Let's see. Can I do the size of the address of star P? I don't know if you can do that. We'll see. Yes, you can. Okay. Of course. That's 8 bytes. Yes, because it's a 64-bit system, so that makes sense. Okay. Yeah, I'm starting to really get this. Starting to understand the memory and stuff. Changing pointers. So we saw how we can add an integer to a pointer in the previous section. This time, let's modify the pointer itself. We can just add or subtract integer values directly to or from any pointer. Let's do that example again, except with a couple changes. First, I'm going to add a 999 to the end of our numbers to act as a sentinel value. This will let us know where the end of the data is. Sentinel value. Sentinel value? Sentinel value? Sentinel value. Sentinel value is programmed to indicate the end of data or to a signal condition. Yeah, that's what I thought. It's a signal value. Oh, by the way, we're at 92 subscribers now. Only 8 away from that 100 subscriber goal. We get to that 100 goal, and we'll have a little dance off or something, a little dance video or something. So if you like what you're seeing, please do go ahead and subscribe. Let's get back to the program. Okay, subtract. We saw how we can add integer. This time, let's modify the pointer itself. You can just add or subtract integer values directly to or from any pointer. Let's do that again, except with a couple changes. First, I'm going to add a 999. Okay. You're going to add a 999 to the end. 999. And we're going to delete. Okay, points to the 11, of course. Now let's start incrementing P so that it points at subsequent elements of the array. We'll do this until P points to the 999. That is, we'll do it until star P is equal to 999. Okay. So now we're going to increment the pointer till we hit the sentinel. Wow. Star P is not equal to 999. Because that's how you dereference. Then we're going to print it. %d, %n, dereference P, P++. Try this out. There we go. 11, 22, 33, 44, 55. Let's comment out the other stuff there. There we go. There we go, there we go, there we go. There we go, there we go, there we go. There we go, there we go, there we go. We're going. Here we go. All right. So, that worked. Pretty crazy. No, not pretty crazy. Pretty cool. When we give it a run, first p points to 11, then we increment p and it points to 22, and then again it points to 33, and so on until it points to 999, and we quit. Subtracting pointers. You can subtract a value from a pointer to get to the earlier address as well, just like we were adding to them before. But we can also subtract 2 pointers to find the difference between them. Example, we can calculate how many ints there are between 2 int star int pointers. The catch is that this only works within a single array. If the pointers point to anything else, you get undefined behavior. Remember how strings are char pointers in C? Let's see if we can use this to write another variant of string length to compute the length of a string that utilizes pointer subtraction. The ideal is that if we have a pointer to the beginning of the string, we can find a pointer to the end of the string by scanning ahead from the null character. Makes sense? And if we have a pointer to the beginning of the string and we compute the pointer to the end of the string, we can just subtract the 2 pointers to come up with the length. Yes, 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 yes. Return. My string length. Remember that you can only use pointer subtraction between 2 pointers that point to the same array. Right, because it's going to be... Yeah, that makes sense. That makes sense. To me. Does it make sense to you? Because a pointer is just a contiguous, or a pointer is just a place pointing at in memory. An array is a contiguous space in memory. So, you know, if I start at 0 to 10, that's at that space 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can subtract 8 from 0 and get the number 8 for the length. But if one part of my array is in 0 to 10, another part is in 25 to 30, then that doesn't work. Because, you know what, let's just draw it out so I can show you what I'm talking about. How's that work? Because I think this is important to understand, but it's also, it makes sense when you think about it, right? So let me change the page paper to white. Plugin manager, are there any plugins? Cycling through color list. Is there a dark? Is there a dark mode? Just a dark mode? Let me see. Help. Let's look a bit of a side. Oh, I'm on my other screen. I'll bring it over here so you guys can see it. I'm looking to see if there is a way. Where's dark? Is there a dark mode? Oh, I don't want to edit the page, but I want it to be dark. What? Let's just do that. Okay. Is there a dark for me? Dark mode? Theme? I guess there's not. I guess we'll just have to do it manually. Sorry about it. It does look kind of gross right now. Let me go to page background. Paper color. Boom. There we go. Okay. So okay. Make sure I'm choosing white as the color. Okay, so remember we said that memory is just a big long array, you know. Let's just do example 0, 0, you know, like 0.01 dot 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 all the way up to, let's say it was, so let's say for the, in this example, there's only 250, example 255, I'm sorry, that would be 256, 256 bits, right? Right, this one's a bit. Bytes. Yeah, 256 bytes, not bits. Okay, so each byte, 256 bytes. So let's say somewhere around here, I'm gonna change this to decimal now, just so it makes more sense. So we're looking at decimal here, right? So we're looking at decimal. So say we're at like memory location 2, 3, 4, 5, 6. Right, and we have an array, say an array of 4, right, and that's pointing towards that memory location. And then we go on further, dots, 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 like this one would be X, F, A, B, C, D, F, A, B, C, D, E, F, E, right? And then the next one, and let's say here we have another one, and it's hypothetically, we're using the decimal again to show you 10, 11, 12, 13, 14, right? And you have another array here that is let's say it's a array B, and it's also 4 items, right? And it's the 10, 11, 12, 13. Well, so the array that might have a pointer here, let's say it's a pointer P, and it's pointing towards that 2 right there at that point. And let's say this is a pointer Q, and it's pointing towards that 10 at that point. Well, if I go to the end of this, so if I say this one's pointer's 2, so the address is 2, right? And I go to the end of this one, and I get to 13, so then int star Q is the 14, then 14 minus 2 is not equal to 4, because we have all of this space here that's not considered because we've jumped in the memory addresses. So I hope that makes sense. I just, writing it out helped me make sense of it right now, so I'm hoping that makes sense to you. And yeah, let's get back into it. Yeah, that makes sense. Array pointer equivalence. We're finally ready to talk about this. We've seen plenty of examples of places where we've intermixed array notation, but let's give out the fundamental formula of array pointer equivalence. B index of A is equal to dereference of A plus B. Study that. Those are equivalent and can be used interchangeably. I've oversimplified a bit because in my example, A and B can both be expressions, and we might want a few more parentheses to force order of operations in case expressions are complex. The spec is specific as always, declaring in C11. Index E2 of E1 is identical to dereferencing E1 plus E2. But that's a little harder to grok. Let's make sure you include parentheses if the expressions are complicated, so your math happens in the right order. This means we can decide if we're going to use array or pointer notation for any array or pointer, assuming it points to an element of an array. Let's use an array and pointer with both array and pointer notations. Okay, so let's do this one here. So that's our same thing there. Okay, we do have the sentinel. So let's just leave the sentinel logic in. With pointer A points to the first element, print all the elements of the array a variety of ways. I would need to say here now that P equals A again, right? To set over, and then I could say for int I equals 0, I is less than 6, I plus plus, and I print %d, printf, %d, %d, new line, and we're printing this with A to I. Okay. And then let's set C style, C set style, K and R. Okay. And then let's grab this. Oh, I thought I grabbed it. There we go. No. How do I mark region? Mark region. Mark. Did I not start a mark? Oh, mark activated. Okay. And then we have how many of these? 1, 2, 3, 4, 5. Okay, so each one, and then this one is doing, oops. This one is doing it P to the I. Okay. And this one's doing it A plus I. This one's doing it P plus I. This one's doing it. This is moving the pointer now again. P plus plus. Okay. Pointer notation with P pointer. Okay. Compile. Oh, we can't do the initial loop declaration. Oh. Go. Sweet. They all do come out. Now let's study. Let's study. Let's study. We've got to study. To make it today, we've got to study. How do you want to study it right now? So you can see that in general, if you have an array variable, you can use pointer or array notation to access elements. Same with pointer variable. So in the first one, we did array notation, and then array notation with the pointer. This one should be dead. Pointer notation with the A. Pointer notation with the P. Move pointer P. Pointer notation with A. Let's look at that one. So this one. This one is like that. Star P plus 1. Oh, it should be P plus I. So what did that print out? Two, 22, so that was wrong. That was just all 22s printed out. So here, we could say printf using wrong 1. Printf end of wrong 1. Recompile. Okay. Yeah. See, it was all 22s. That was wrong. Okay. So it's supposed to be an I. P plus I. Supposed to be I, supposed to be I, supposed to be I. Hello everybody, how are you doing? I am talking to myself because there's nobody on the stream. 0 people. Actually shows one person. Okay. Pointer array notation, same with pointer variable. The one big difference is that you can modify a pointer to point to a different address, but you can't do that with an array. In other words, you can't assign into an array variable at all, only into individual elements of that array. Right, because then you would mess up the whole contiguous memory thing that we were just talking about with external. This makes sense. If you really want to copy one array to another, you have to use a function like memcopy or a loop to make that happen. Array pointer equivalence function calls. This is where you encounter this concept the most, for sure. If you have a function that takes a pointer, example, int my string length char pointer, this means you can pass either an array or a pointer to this function and have it work. Char s antelopes, char pointer wombats. My string length works, and it's also why these two function signatures are equivalent. Okay, that makes sense. Void pointers. You've already seen the void keyword used with functions that indicate no parameters or no return value, but this is an entirely separate, unrelated animal. A void is definitely a pointer to an existing thing, but the void part of it indicates that we don't know the type of the thing. And sometimes, believe it or not, that's really useful. It enables us to write code that's a little more type agnostic, which is some nice flexibility to have in a typed language like C. There are basically two use cases for it. Let's check them out and see if we can demystify it a bit. A function is going to operate on something byte by byte. For example, memcopy copies bytes of memory from one pointer to another, but those pointers can point to any type. Memcopy takes advantage of the fact that if you iterate through char's pointers, you're iterating through the bytes of an object no matter what type the object is. More on this in the multi-byte values subsection. Okay, a function is going to operate on something byte by byte. For example, memcopy copies bytes of memory from one pointer to another, but those pointers can point to any type. I see. Takes advantage of the fact if you iterate through chars, you're iterating through the bytes of an object no matter what type the object is. More on this in the multi-byte value section. Because it's 1, right? Because the char is 1. Because the char is 1. Because it is. Because it is, guys. The size of the char is 1. It is. Do you want to see? I promise you. I'm not lying. It's 1. Why is it showing? Why does it not show it at all? Oh, because it's not enough space. Size of a char is 1. It's 1. What did I forget again? I didn't forget to put the new line in there. I always forget the new line. I'm definitely gonna have a. Oh, I wonder how. Like, we'll have to get some emojis or something. I'm thinking about moving the stream towards like Twitch as well, but I don't know how to use Twitch. I mean, I've had Twitch before, but I don't really know how to use it. Maybe tomorrow morning we could do like a test stream in Twitch. I wonder if I could do. Can you stream to 2 places at once? Can I stream to YouTube and Twitch at once? I'm not sure. Okay. So a function is going to operate in something. Another function is calling a function you pass to it. There are basically 2 types. Check out. Another function is calling a function you pass to it, a callback, and it's passing you data. You know the type of the data, but the function calling you doesn't. So it passes you voids, pointers, because it doesn't know the type, and you convert those to the type you need. The built-in qsort and bsearch use this technique. Let's look at an example of the built-in memcopy function. Another function is calling a function you pass to it. Basically, let's check them out. The void pointer, there are basically 2 use cases. Another function is calling a function you pass to it, a callback. Calling a function you pass to it, and it's passing you data. You know the type of the data, but the function calling you doesn't. So it passes you void stars, void pointers, because it doesn't know the type, and you convert those to the type you need. The built-in qsort and bsearch use this technique. Let's look at an example. The built-in memcopy function. This function copies n bytes of memory starting from address S2 into the memory starting at address S1. But look, S1 and S2 are void stars. Why? What does it mean? Let's run more examples to see. For instance, we could copy a string with memcopy, though string copy is more appropriate for strings. Or we can copy some ints. Okay, so this is a bit of a section. Whoa, this is a real big of a section. Okay, so let's take a small break. Let's take a small break. and we can, let's take a small break, and when I get back from the break, then we'll take a look at doing the understanding of the void function pointers, which should be very interesting. I'm real quick, yeah, let's take a small break, and then we'll do that. So yeah, I need to edit the break real quick. Give me 1 second here. Shoot, I don't have it. Okay. Sorry, guys. Okay, we'll take a 5-minute break, and then I'll be back after that, and we can start on the other work there. let's get back to it. How about that? How about that, guys? We get back to it? Should we do some of the Emacs configuration stuff, or finish with this void pointer? We could do the one. Let's do one example of the void pointers. We won't finish the whole thing today. Maybe tomorrow, or whenever the next stream is, and then we'll just play around with a little bit of Emacs configuration, because I haven't done that in a long time. I'm actually just kind of really getting back into my Emacs crest of things. So yeah, that's what we'll do. So here we are back in the screen for where we were, and let's go ahead and continue on. All right, so void men copy. So what I want to do is I want to look at the man again. You know, I'm always manning it. Mem copy. That's a pretty small. That's a pretty small man doc. Look at that. That's 2 pages. 2 pages. Wow. Okay. The memcopy function copies n bytes from memory area source to memory area destination. The memory areas must not overlap. The memory areas must not overlap. Are you? Of course, the memory areas must not overlap. I mean, that makes sense, though. Look, I'm not an expert. I'm not an expert, so I shouldn't be assuming that's a dumb statement to say, but it seems pretty silly, because the memory they can't overlap, because how can you copy one thing over to another when you're going to be copying yourself over to the thing? That doesn't make sense. And it is a void and a size. Okay. Void and a size. Yep, size t. Function copies. Okay, so let us mess with it then. Pointer C. Let's just let's go. Okay, I do have to. Since I don't want to do a whole new file today, let's just do char s, right? Like they're doing, and say goats. They like goats, and we'll do char t of 100 bytes, or 100. Yeah, 100 bytes. Chat. Good old chat. Good old chat type. Char. And then I'm going to do mem copy. Why do we need string.io for that? The string.io standard C. Oh, it is in mem. But that's very interesting that it's in. Huh. Include string.h. That is weird that it is in string. But I guess it's something you would want to use with strings often, right? Okay. Mem copy T S copy into TS. Mem copy into TS, and it is the size of 7. Printf %s n, and then we're gonna print the T now. Okay. Recompile. Warning, memcopy is reading 7 bytes from a region. Oh, we need the goats. We need the goats to be goated. They have to be goated. There we go. No. I want term. There we go. Goats. Ma. Ba. 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 Do you like my baaing? Ba. Ha. Ha. Ba. Okay. So, we did that. And it worked. Or we can copy some int s. We can copy some ints. Oh. Size of... that one's a little wild. You see what we did there? With memcopy, we copied the data from A to B, but we had to specify how many bytes to copy. And an int is more than 1 byte. Okay, then how many bytes does an int take? Answer, depends on the system. But we can tell how many bytes any type takes with the size of operator. So here's the answer. An int takes size of int bytes of memory to store. And if we have 3 of them in our array, like we did in that example, the entire space used for the 3 ints must be 3 times size of int. In the stream example earlier, it would have been more technically accurate to copy 7 times size of char, but chars are always 1 byte large by definition, so that just devolves into 7 times 1. We could even copy a float or a struct with memcopy, though this is abusive. We should just use equals for that. This is abusive. Don't know. Okay. Let's stop there for... Why is it saying it's abusive? So if this is abusive, we should just use equal for that. But does structs equal structs? Let's go back to the contents for a minute. Comparing structs. Just assign one to the other. This is not a deep copy. All fields are copied as this, including pointers to things. A deep copy follows pointers in the struct and copies the data they point to as well. A shallow copy just copies the pointers, but not the things they point to. C doesn't come with any built-in deep copy functionality. I see what you're saying. Our fields are copied including pointers to things. You might think you could use memcopy, but that doesn't handle the case of the possible padding bytes that might be in there. Okay. That makes sense then. That makes sense. Okay. Look at how versatile it is. If you have a pointer to a source and a pointer to destination, you have the number of bytes, you can copy any type of data. Imagine if we didn't have void, we'd have to write specialized memcopy functions for each type. Much better to use void star and have one function that can do it all. That's the power of void star. You can write a function, void pointer. You can write a function that doesn't care about the variable's type and is still able to do things with it. Kind of like polymorphic? Is that like polymorphism? From like my OOO days? My OOO days? Is that polymorphic? Seems like it might be polymorphism. Is it? But with great power comes great responsibility. Maybe not that great in this case, but here are some limits. You cannot do pointer arithmetic on void pointer. That makes sense because you don't know the size of the thing. How are you going to arithmetic something? You cannot dereference a void pointer. Also makes sense because you don't know what you're dereferencing. You cannot use the arrow operator since it's also a dereference. You cannot use array notation since it's also dereference. And if you think about it, these rules make sense. All those operations rely on knowing the size of the type of data pointed to, and with void pointers, we don't know the size of the data being pointed to. It could be anything. But wait, if you can't dereference a void pointer, what good can it ever do you? Like with memcopy, it helps you write generic functions that can handle multiple types of data, but the secret is that deep down you convert the void pointer to another type before you use it. And conversion is easy. You just assign it into a variable of the desired type. Char a equals x, void pointer p is the address of a, char q equals p, print error cannot dereference void, print prints x. Let's write our own memcopy to try this out. We can copy bytes, char s, and we know the number of bytes because it's passed in. Void my memcopy, void destination, void source, and byte count. Convert void s to char, char s equals source, d equals destination. Now that we have char s, we can dereference and copy them. While byte count negative negative. Yep. It's the truthy value. It's 0 would be a false value. While type count, byte count negative negative. Dereference dd equals dereference to s. Most of these functions return to destination just in case. That's useful to the caller. Do they return? Does the memcopy do that? Oh yeah. Returns a pointer to destination. Okay. Even though you already have the pointer at destination, right? Okay, what's the next step? We did pointer arithmetic, manual memory allocation, nullify all objects, outside environment. Okay. Let's go to our init file now then. Let's do some init stuff, .emacs.d, init. Okay, so these are some UI changes. So is that big enough for you guys to see? Let me make it bigger. Okay. Toolbar mode, menu bar mode, scroll bar mode, menu bar mode, toolbar mode, scroll bar mode, eval buffer. Okay. Gives us a lot more of an open area. And then we could say, let's do themes, setup for themes. So I could say use package, space max theme. Oh, I need to do add to list though. I have to do the add to list. Let's go to Melpa. 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 Not Melpin. Melpa. Melpa. And Getting started. Add to list. Package archives. Why do we need to require package? Do we need to have... Let's see, I don't because this is Emacs 30. Can't we just do setup package archives? Can't we just do add to list package archives? Melpa https melpa.org packages void variable package archives. Okay, so we do need to require package. Okay, package refresh contents. Package initialize. Okay, let's do list packages. Package refresh contents. Package refresh done. Okay, so Spacemax theme. Spacemax. Package refresh. Package refresh. Contents. Okay. So we should have a bunch. Yeah. Okay, so Spacemax theme. There it is. Spacemax theme. Okay, so if we go back, we should be able to do Spacemax team, ensure T. Failed to parse, wrong type argument, Spacemax theme. What? Let's see, use package. Examples. Is there examples here? Examples, use package foo. Oh. You don't need to do that? Okay. Okay. Theme, custom describe theme, display, enable theme. Init. The init. Where's the init? Init. Configuring packages. Init is evaluated before loading a package. Is it now? Okay. So we need to config. Enable theme. Failed to parse package, wrong type. Oh. Symbols, values, variables, void. Enable theme. Load theme. Ah. There we go. Okay. How's that look? Does that theme look better? I think that theme looks good. That's the Space Max theme. I kind of do like the Space Max theme. Okay. So, and then we want which key. So use package, which key, ensure T, init, which go. Look at it, we got which key now installed. Cool. Cool, cool, cool. Cool, 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 cool. Oh, oops. So there's some more changes to our Emacs there. Key, and I also like beacon, use package, beacon, user package beacon, use package beacon, use package, beacon, ensure T. Look at that. Now we got beacon, so it tells us, shows us where our line is really quickly there. Okay. All right. So that is some Emacs configuration that we've done now. Hope everyone is having a good night. I think we'll get ready to wrap up for this evening. We'll get ready to wrap up for this evening and move on to plans for the next couple of streams. What I would like to do is continue on with C, do a little bit more of some Emacs configuration, maybe start to program something a bit useful, get an idea for like a tool or something, or like for something that I could use the standard input and output streams within like the existing Unix tools. Kind of just mess around with stuff and build something cool. So thanks for joining today. If you liked what you saw, go ahead and smash that like button, subscribe. The name is not Primogen. I'm not Primogen. Keenan can do. And come and join me next stream and let's find out what all of us can do together. Bye, everybody.